So guys, I'm going to be taking you through the beautiful journey of mastering the limits of function problems at infinity. So that is basically we're going to be looking at three special cases of limit at infinity. So now we have three special cases of limit at infinity. If you can understand this, then you can understand how to solve limit of function at infinity very easily without stressing. We have the first case written down here, and the first case here is we say when the limit of the function f of x over g of x as x approaches infinity, when our answer is equal to infinity, it simply means the degree of the numerator, which is f of x in this case, is greater than the degree of the denominator, which is g of x at this case. So we refer to that as top heavy. You can just use top heavy to cram it, which is easy, because the top heavy here in this case means the degree of the numerator is greater than the degree of the denominator. We can just see the degree of f of x is greater than the degree of g of x, which is the numerator. So basically this is the what? Denominator. Basically this is the numerator. So we can see the degree of the numerator is greater than the degree of the denominator. So we are going to be looking at examples so that we can understand this better. So for now, let's do a recap over it. We say the first condition here says for a rational function, which is as well a polynomial function, because in most cases these two will be polynomial functions, but not in all cases though. So where f of x is the numerator and g of x is the denominator, that is a rational function, for a limit as x approaches infinity, if we have the answer infinity, if we substitute infinity into the rational function and we still have infinity as our answer, that tells us that the degree of the numerator is greater than the degree of the denominator. So whenever you are solving such a question, your answer is just going to be infinity, no matter how long the process looks like. So let's take an example so that we can understand the jargon we have said so far. By the time we begin to apply it on questions, you'll get to understand what you are saying better. So let's take an example where the degree of the numerator is greater than the degree of the denominator. So let's take, for instance, the function where the limit as k approaches infinity for the function 2k cubed minus k squared plus 4 over k squared plus 5k. So looking at this now and applying this principle, applying this case or applying this condition to this question, our answer is going to be very straight without wasting time. Our answer, we have to first of all identify whether this satisfies this condition. If this is our f of x and this is our g of x, you can see now we've balanced it. This is our numerator and this is our denominator. Which one has a higher power? Which of them has a higher degree? Obviously the numerator has a higher degree, which is 3. The highest power here is 3 and the highest power here is 2. So that simply tells us that we all know that 3 is greater than 2, which simply means f of x, which is the numerator, is greater than the denominator, which is g of x. And that is, we can just rewrite it as the degree of the numerator, which is d f of x, is greater than what? d g of x. So what is going to be our answer? Our answer is going to be as simple as this. Mere looking at this, we say when we have the numerator having a higher power or having a higher degree than the denominator, our answer is simply going to be infinity. So mindful of all the values you have here, so long as the numerator is greater than the denominator and the limit is at infinity, our answer is definitely going to be infinity. And it is as simple as that. But if you want us to prove it, we can also prove it and know why we got to such an answer. and that's very simple. Let's walk through proving this and see if we get this. I know some of us will be very curious and we really want to know why we just jumped from this to this, and why we concluded that so long as the limit is at infinity and the numerator is greater than the denominator, we have infinity. Some people want to really know why we just arrive at this answer. So for the sake of that curiosity, let's try to solve this and see if we are going to get infinity as our answer. And of course we are going to get infinity as our answer. So let's walk through it together. Now, simplifying further, to get this done, we have to, before substituting the value of infinity, or before substituting the value of k, which is infinity, into this function, what we are going to do is we are going to simplify. And to simplify this function, we are going to divide all through both the numerator and the denominator by k cubed. We are dividing by k cubed because we want to do away with k cubed. We want the highest factor to go away. And doing that, we have 2 divided by k cubed. We do the same for all other factors, which gives us k squared over k cubed as well, plus 4 all over k to the power of 3 as well. Then for the denominator, we'll do the same. K to the power of 2 divided by k to the power of 3 plus 5k divided by k to the power of 3. So we have successfully divided by k to the power of 3 all through. So having done this, we are going to be getting 2 minus k squared over k3. It will definitely be 1 over k left. And for this one, it will be 4 over k to the power of 3 left. Then we divide all through by what is here. And here will be 1 over k plus 5 over k squared. So this is what I'm going to be getting. So this is the simplified form. K still approaches what? Infinity. So let us substitute the value of infinity into this simplified function. Substituting the value of infinity into this new function or simplified function that we are going to be having 2 minus 1 over infinity plus 4 over infinity cube. Of course, we know infinity cube is still infinity because infinity could be a very big number in this sense. And 1 over infinity plus 5 over infinity squared. So these are resulting function. But before then, remember that a constant over infinity is only going to give you 0, because infinity here could be 1,000. Let's take infinity to be 1,000, because infinity is not necessarily something you don't know. It could be something you know, but it's a very, very big number. Let's say 1,000. So 4 over 1,000 will definitely give us 0.004, which is approximately 0. So a constant over infinity is always going to give you 0. Just remember that. Okay, so now that we have 2 minus 0 plus 0 is going to be 2. So basically we are going to have 2 over 0. And we said 2 over 0 is a constant over 0. A constant over 0, just recall that a constant over 0, any constant over 0 is going to give you infinity. And now we've arrived at this point where we left. So for those who are curious about how this got to this, you can see the working. So what we did is we simplified this. Before we substitute directly, we simplified this to this by dividing all through by the highest power, which is k cubed. Now after dividing all through by k cubed, it was simplified to this. After being simplified to this, we have this. Now we substitute the value of k into this, and it gave us this. And we said 1 over infinity is 0. A constant over infinity is 0. 1 is a constant, 4 is a constant, 1 is a constant, 5 is a constant. So all these ones that are over all these constants over infinity become 0. So 0 becomes 0, 0, 0, 0. And any constant over 0 is going to give you infinity. And that's why we have infinity. Okay, so let us take a look at this example so that we can understand the second case better. In this case, both the numerator and the denominator have the same degree. So since they have the same degree, the answer is going to be the coefficient of the term with the highest degree in the numerator, which is 2k to the power of 3. The coefficient of 2k to the power of 3 is 2, and the coefficient of k to the power of 3 in the denominator is 1. So that's going to be our answer. So 2 over 1 is 2. So this is simply our answer. So what have we done here? If you look at the numerator in this case, the highest term here is 2k to the power of 3, and its coefficient is 2, so pick out the 2. When we look at the denominator, which is having equal highest power as the numerator, in this case now, the highest power in the numerator and the highest power in the denominator are equal. For that reason, since they are equal, our answer is simply going to be their coefficients, which is 2 over 1. There's a 1 here in case you don't know. So how do you know that 2k to the power of 3 is the highest? 3, 2, 0. So you know that this is the highest term, this is the highest term. So their coefficients are going to be the answer. So 2 over 1 will be the answer to this. But we can prove it for those of us who are curious about knowing how we arrived at this. But if you take the same step we took solving for the case, for the first case, you are going to get it this way. All you need to do is to divide all through. You simplify this further by dividing all through by k cubed. So let's try to solve this and get this answer using the log method. Okay, so now we want to also prove that, just as we said now, that for this function 2k cubed minus k squared plus 4 over k cubed plus 5k is equal to 2. So we want to prove that whenever we have the powers of the denominator or the degrees of the denominator and the numerator equal, our answer is going to be the coefficient of the terms carrying the highest degree. The term carrying the highest degree in the numerator is 2k to the power of 3, and its coefficient is 2. The term carrying the highest degree in the denominator is k to the power of 3, and its coefficient is 1. So 2 over 1 is going to give us 2. So we want to prove that whenever I see such an example, all we just have to do is to pick the coefficient of the highest terms. We want to prove that that's actually the standard thing to do. So let's see why that's the standard thing to do. So how do we simplify this? All we have to do is to divide all through by the highest term. Divide all through by k cubed. So what I'm going to do is, so let's take it this way. Divide all through by the highest term. What's the next thing to do? So let's cancel out the ones that can cancel out and see what is left. So doing that, this will go, and here 1 will be left. So we have 2 here minus 1 over k plus 4 over k squared all over, and for the denominator it's going to be 1 plus 5 over k squared. Remember, your limit still tends to infinity. So what you are going to do is to substitute infinity into this new function that we have, this simplified function that we have. So the first thing we did is that we simplified by dividing the numerator and the denominator by k to the power of 3. And after doing that, some terms have cancelled out, and what is left is this. So substitute the value of infinity, the value of k into this, and see the resulting answer. So just like I said earlier on, if we substitute the value of k, which is infinity, into this equation that we have, into this function that we have, we get this 2 minus 1 over infinity plus 4 over infinity squared. Infinity squared remains infinity. I said infinity in this case could be 1,000, 2,000, 3,000. 2,000 squared gives a very big number, or a bigger number, which is still infinity in this sense. So a constant, I said you should recall that a constant, any constant at all over infinity is going to give you 0. Now that we know that a constant over infinity will give us 0, we have to use it here. And we said why a constant over infinity will give us 0 is because infinity is a very, very large number. So let's say 1,000 here. If we do 4 divided by 1,000, we are going to get a value that is almost 0. So in this sense, we are using 1,000 as infinity, or a number that is very close to infinity, since we say infinity is a very, very large number. So dividing 4 by a very large number, let's say 1,000 or infinity, will give you 0 in all cases. So in this case, here will become 0, here will become 0 as well, here will become 0 as well, and what you have left to be 2 minus 0 plus 0 over 2 over 1 plus 0. This will leave us with our answer as 2. So now, getting this answer as 2 brings us back to this place where we started from, where we said the limit as it tends to infinity will give us 2. So this gets balanced, and I believe it is got to. So that is why. So for any random question you see, all you just need to do is to take the coefficient of the highest term in the numerator over that of the denominator, and that will be your answer. There's no need of going all through this stress. We are just doing this just to prove that whenever you see a limit of a function, hence the limit tends to infinity, and the power of the numerator and the denominator, that is the degree of the numerator and the denominator, are equal, it means what you are going to do is just to pick the coefficient of the highest term in the numerator over the coefficient of the highest term in the denominator, and that's what our answer is going to be. And in this case, the answer is 2 over 1, and that's why we have 2, and we've chosen to prove it. So this is the second case. So there's the third case. So whenever I see this kind of stuff in your exams, you don't have to go through all this process. All you just need to do is look at the one with the highest power, look at the one with the highest power in the numerator, look at the one with the highest power in the denominator, and pick their coefficients over each other. And that is 2 in this case. And that is why. So we just did this to prove, for those who are curious about knowing how we got 2. So I believe so far we've learned that the constant over infinity is 0, or almost 0, since infinity is a very, very large number. So let us write through the last case, which is the third case. And this case basically states that if you have a rational function and the limit tends to infinity, where the limit is at infinity, after substituting the limit, which is infinity, into the rational function, and you have 0, it means the condition that is at play there is that the degree of the numerator is less than the degree of the denominator, which n is less than d, or f of x is less than g of x. So I refer to such a situation as bottom heavy. And just remember that for a bottom heavy you have 0. For the first case we call it top heavy, because it is top is the numerator that is greater. That's why I call it top heavy. But in this case, the denominator is bigger. That's why I call it bottom heavy. So we are going to write through an example so that we can understand what this is saying. It's just like every other one. Hence, the denominator is larger, our answer is going to be 0. We'll pick an example and also prove through the example and see how it goes. Take this example into consideration for this third case. It's such a beautiful example that you will all love. So let's consider the limit as k tends to infinity for 2k to the power of 3 minus k squared plus 4 over k squared plus 5k. I know a lot of you are already wondering which of these two has a higher degree, whether the numerator or the denominator. But it's quite easy, and most of you also concluding that the numerator has a higher power and doesn't satisfy this condition. But that's not the case at all. Whenever you see a function carrying a square root, it's always lesser than the one not carrying a square root, because in this case here, this is a square root. Now let us consider squaring 2 and making a square root of 2. Which of them will give us a bigger number? Well, let's say 4. If you are to take the square root of 4, you will get 2. The square of 4. 4, you will get 16. So 16 is bigger than 2. So square and square root are opposite, but square will always go exponentially, while square root will always give a little value. So square is bigger than square root. So this actually satisfies this function. What I'm trying to say in essence is that this value without square root is actually bigger than this with square root, because I just made a practical example now. Let's assume 4 root 4 is what is here, and 4 squared is what is, and 4 squared is what is here, because here has a square, but here has a root. So squaring this, you get 16. If you can find the square root of this, you get 2. This one takes the value down, this one takes the value up. So square is actually very big, while square root is small. I hope you get the ideology. So this is actually bottom heavy, because the function which is at the denominator is bigger, since it is a square. It's a square function, while this one is a square root function. And the square root function will always take the graph. If when plotting the graph, the square root of this. So I said let us use a number to study the behavior of square roots and squares. Now this is a square root function and this is a square function. Now we used 4 for instance. This is just an example. So let me put stuff there. I'm just trying to explain this. Now square root of 4 gives you 2 and the square of 4 gives you 16. This comes down, this goes up. You can see this is a graph of a square, this is a graph of a square root. Now if you pick a function, let's say f of x, and you square the function, this is how the graph goes. And if you square root that same function, this is how the graph also goes. So dividing 2 by 16 will give almost 0. That's 1 by 8. That's 0 point something. And you can see that it's almost satisfying this already. So if we use a bigger number, let's say 6 here, square root of 6 will be very minimal. Square of 6 will be 36. Dividing it will be giving you almost 0. Dividing a small number by a very large number, just like I said infinity, will be giving you 0. Just like giving a piece of biscuit to 1,000 people, it will mean almost nothing to them. It is synonymous to dividing 2 by 16, which will be approaching 0. This will actually approach 0. So that's why this function goes this way. From the 3 cases we just looked at, that is the 3 cases where the limit tends to infinity for a rational function that we just looked at. Let's evaluate the limit. Tends to infinity for the function k cube plus 5k 2k cube k square plus 4. So now this question exhibits the properties of one of the cases we just talked about, and that is the third case. When the highest power of the numerator is equal to the highest power of the numerator, the answer is going to be the coefficient of the variable with the highest power of the numerator over the coefficient of the variable with the highest power in the denominator. So basically, what that big English means is this. If you look at this, the highest power here is 3. If you look at this, the highest power here is also 3. Now, the highest power in the numerator and the highest power in the denominator are equal. And since they are equal, we are going to take the coefficient of those variables carrying the highest power as our answer. What the big jargon is simply saying is that our answer here is, since there's 1 here, our answer is 1 over 2. The coefficient of k cube here is 1. The coefficient of 2k cube is 2. But this is for the what? Second case, where, so basically, in this case, the numerator is equals to the denominator when it comes to power. So that's what our answer is. You can see how simple this is.